Good afternoon. So today we're going to do more differentiation from chapter 12 in the Pure Book. This time I've corrected my slide so it does read as differentiation. Before there was a little typo, well done if you spotted it, and extra well done for not showing me up in the comments by correcting it, but you could have done. Anyway, so let's have a look at some more of this differentiation starting from first principles. So we're going to start off, as you can probably guess, with a warm-up of 4 questions, as per usual, like we do in class. So here are the 4 questions. What I'd suggest you do is to either print off a worksheet if you can from the Padlet. If you can't, if you don't have a printer, just jot down these warm-up questions and have a go at them. When you think you've got the solutions to them, play again the video and see if your solutions match mine, which I'm going to go through now. Okay, so let's have a look at question 1. Question 1 is a recap from the other lesson, where we're going to prove from first principles that the gradient function of x squared is 2x. So we can always define the gradient function, f dashed of x, as the limiting case when h goes towards 0 of f of x plus h minus f of x, all divided by h itself. So here, f of x plus h, where the function is just squaring the input, that's going to be x plus h all squared. So we need to expand the binomial, but that shouldn't be any problem to us really. F of x is x squared, and at the bottom we've got this h, which we'll see will help to cancel out some of the top terms. So the good thing about this is you do become an expert at writing the word lim. Anyway, x plus h all squared is x squared plus 2xh plus h squared minus off the x squared all over h. And so what happens here at the top is the x squared will cancel, and we'll just be left with 2xh plus h squared all over h. And so this here will cancel. 2xh over h will become 2x. H squared divided by h will just leave us with h. So as h goes towards 0, the value of h will shrink down, and so the absolute limit as h goes towards 0 of the gradient function will just be 2x, like we saw in the previous lesson. Question 2, prove from first principles that the derivative of any constant, let's call it c, is 0. So we've been given a hint here which we can use, just let f of x equals c. So from first principles, f dashed of x is just going to be the change in y in the limit that h goes towards 0. As always, the change in y is going to be f of x plus h minus f of x all over h. So let's just plug in these values. Now we are told that this is a constant function. It's never going to change. And so the function is always going to be c no matter what. And so the function where we input x plus h is just going to map to c. And so f of x plus h will be c. F of x will also be c, because the function is never changing. It is by definition the constant c all over h. So no surprises, the top of this fraction is 0. So 0 over h is just 0. Anything, if you divide anything, if you divide 0 by anything, it's obviously going to be 0. And so the limit as h goes towards 0 of 0 is obviously just going to be 0. And so that's question 2 done. Question 3, we need to show that the expansion of x plus h all to the power n can be written as this thing here. And so what we're going to do here is just recall our old friend, the binomial expansion, which is as follows. So what we need to do is write down the binomial expansion in its first principle form. So x plus h all to the power n. Now, if the power is n, The binomial coefficient, the first one is n choose 0, and the first term in the binomial is going to be x to the power n. The power of the second term, in this case h, is always going to be the same as this bottom value, in this case 0. Then as we go along, the bottom value increases by 1 each time. So the first one will be n choose 1. What happens to the value of the power of the first binomial term? This goes down by 1 each time, so we have n minus 1. The power of the last term in the binomial increases by 1 each time. You should recall that the sum of the powers of these two will always equal the value of this thing here in the binomial coefficient. So that's the first one. Going on, we had n choose 0, n choose 1, now it's going to be n choose 2, x to the power n minus 2, h will increase from 1 to 2, and so on and so forth. Hence these dots, this ellipsis, dot 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 just means and so on and so forth. So this pattern will keep on carrying on until eventually we get to n choose n. This power of x will decrease all the way down to 0, and the power of h will increase all the way up to n here. And so if we just neaten this up slightly, n choose 0 is always going to be 1. So we're just going to have x to the power n. Anything to the power 0 is just 1, so xn times 1 just gives us x to the power n. N choose 1 will always be just n. For example, 5 choose 1 will be 5, 6 choose 1 will be 6, and so on. So n choose 1 is n, x to the power n minus 1, h to the power 1 just gives us h. N choose 2, we can't simplify this here, so just let's leave it as n choose 2. We don't know what n is. X to the power n minus 2, h squared, plus dot dot dot. And n choose n is going to be the same as n choose 0, which is again just going to be 1. X to the power 0 is just 1 as well. H to the power n is just h to the power n. And so we get what we needed to end up with, and we've proven what we needed to prove. And question 4. Going back to one of the earlier parts in the course, simplifying indices, the laws of indices, we should be able to remember these hopefully fairly straightforwardly. So part A, x divided by x cubed. When we're dividing indices with the same base, we simply subtract the powers. So x to the power 1 divided by x to the power 3, that's going to be just x to the power 1 minus 3, which will be x to the power minus 2. Part B, the top of this will simplify to x to the power 5. The bottom is x to the power minus 2. So again, in the same way as part A, we have x to the power 5 minus minus 2, which will give us x to the power 7. And part C, we have x to the power 1 on top, and the square root of a value is the same as being to the power half. And so that's x cubed to the half, which is x to the power of 3 halves, 3 over 2. So that's going to be x to the power of 1 minus 3 over 2. That's going to be x to the power of minus 1 half. And so those are the answers to the warm-up questions. So, looking forward, whereabouts did we get up to last time? Let's just consider that now from the previous lesson. What did we prove last time in terms of derivatives? What functions did we work out the derivative of, and how did that link in to the original function? So, just to recap, here's what we had. We had y equals x squared, we differentiated it to this. We had y equals 5 to the power x, which differentiated to 5. Just put an arrow up here as well. F of x, y equals 3x squared. We differentiated that according to first principles and arrived with the derivative function being 6x. And when y was x cubed, we evaluated the gradient function as being 3x squared. So how does this all link in? What's the overarching theme? How can we spot a pattern? Anyway, have a ponder. I'm hoping you might have spotted this yourselves anyway, but if not, it's absolutely fine. I'll give you a bit more of a clue. Just focus on the index, the original power, and the final power. So I'm just going to write these in. So 2x is the same as 2x to the power 1. This here, this power of x was 1. There's no power, there's no x at all here, but consider it, if you will, as x to the power 0. Because that would just be 5 times 1, which is just 5 as well. X squared goes to x to the power 1. So let's just have a look at how the powers change each time, and what happens, in a sense, to the original power. 2, that 1. Does it disappear or does it not? Where does it go? The 2 moves, becomes a 1, but this coefficient now becomes 6. So how does 6 relate to 3 and 2? You get my drift, hopefully, but if not, don't panic. I'm going to try and show you this pattern robustly by proving it from first principles using the binomial expansion, which we know now quite well. So let's just consider the general case. How about where f of x is x to the power n? Let's try and differentiate this from first principles using what we know already about the binomial expansion. So what we've done before will help us in this. So let's just set out, as we do all the time, the definition of the gradient function. F dashed x is always, all day long, the limit as h goes towards 0 of f of x plus h, take f of x all over n. Now, if I can just refresh your memory from before, not too long ago, we just worked out what x plus h to the power n was. So we can use this to our advantage. So this is the same as the limit as h goes towards 0 of x plus h to the power n minus x to the power n all over h. Now this bit we're going to just remember from before how we can define this, what it actually is. So limit as h goes towards 0, x plus h to the power n. Well, we proved this was the same thing as x to the power n plus n x n minus 1h plus n choose 2 x to the power n minus 2 h squared plus dot 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 plus, whoops, not plus, sorry, minus x to the power n. That would have been rather silly, wouldn't it? Anyway, so all of that divided by h. So all I've done here is just rewrote this in its longhand form. All of this thing here minus off x to the power n. And so, as almost always, you're going to see that at least one of these terms on the top will cancel. In this case, we've got x to the power n here, minus off x to the power n over here. And so, if we just neaten this up ever so slightly, we'll arrive at a very neat result, regardless of it looking quite ugly over here. So, we're going to have nx n minus 1 times h. Notice here, the power of h is just 1. In subsequent terms, what we're going to have is the power of h increasing each time. So, for example, over here, we've got h squared, haven't we? So just think about how this will cancel and how many h's would cancel. That's going to go all the way up to plus h to the power n. I didn't include this here but it doesn't matter too much as long as you get the main point that the x to the power n will cancel. So divide that all by h. So the key thing here is thinking, how will h on the bottom cancel with the top, and which terms will not have a h completely cancelled? So hopefully you can spot that the only term where the h will cancel exactly with what's on the top is this first term here, the nx n-1h over h. This one here will become just nx n-1, and the h will cancel. The other terms will have at least one h left. So what we'll have going on is n choose 2 over here, x to the power n minus 2. The power of h will drop by 1, h squared divided by h, we'll just leave with h, plus dot dot dot, and the final power of h used to be n, divided by 1h, that'll just leave us with h to the power n minus 1. But if h is going to go towards 0 in the absolute limit, just think what will happen to all these terms with a h still present in them. Because h is going to shrink down towards 0, all these terms after the original one will just shrink down to nothing. And so all we're going to be left with is the first term over here, nx to the power n minus 1. All other terms will just become absolutely insignificant. So therefore, if f of x is x to the power n, then the gradient function of this, f dashed of x, is going to be nx to the power n minus 1. And that's an incredibly powerful result we'll use time and time again in year 12 and in year 13. And that goes back to what I was hinting at before in terms of a general pattern. So what happens from before, if I just take you back for a moment, is here the power of x essentially moves to the front and multiplies the pre-existing coefficient. So here the coefficient is just 1, so 2 times 1 becomes 2, and the power, the initial power, drops by 1. The 1 comes to the front here, 5 times 1 is 5, then the new power is x to the power 0, which essentially just vanishes, and so on. And so this proves, this is the general form of what we may have discovered earlier ourselves. So that's f of x equals x to the power n. So let's just extend this one step further if we may. Case 2, let's imagine now that we've got f of x is a x to the power n. So again, let's just set it out, give ourselves enough space, take our time, and see what cancels and if we can simplify down these results. So it becomes quite tedious after a while in a nice, predictable way. F dashed x all the time is going to be the limit, as h goes towards 0, of f x plus h minus f of x all over h. Now this time, it's very similar to our previous example, but here we have a multiplicative constant at the beginning of x to the power n. And so what we're going to have here is a multiplying this whole expansion. And so f of x plus h will simply be a x plus h to the power n. Then we'll have over here minus f of x minus ax to the power n all over h. So give myself plenty of space to write this long thing down. So if we just put the a to one side for a moment and consider the expansion of x plus h to the power n. The a at the front is just going to multiply the whole thing through, so I'm going to put this expansion in big curly brackets here. Now I'm going to just essentially copy down what we had before. So this x plus h to the power n is going to become exactly what we had in the previous slide, which is this over here. So rather than waste the time doing the same thing, it's going to be the same as this here. So it's going to be x to the power n plus, then we're going to have n x n to the minus 1 h plus n, choose 2, x to the power n minus 2 h squared plus dot 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 all the way up to h to the power n, and all of this minus axn, and all of this is going to be divided as ever by h. And so if you look over here, we will have another cancellation. So a multiplied by x to the power n will cancel with this thing over here. And so what we're going to be left with, if I just use this space here, is the following. So it's going to be the limit as h goes towards 0 of the following. So the limit's going to be, on the top, we'll have a n x to the n minus 1 h plus a multiplied by n, choose 2, x to the power n minus 2 h squared plus all the way along until we get a multiplied by h to the power n. Now all of this on the top is going to be divided by h once again. And so now we need to consider what we'll be left with on the top after all the top's been divided through by h. And so if we look here, what we'll have is this h on the top here of the first term will cancel exactly with the h on the denominator. And so we'll just be left on the top with an x to the power n minus 1. This h will completely have cancelled. Just emphasize this by crossing out h here and h there. The other h's will have a n, choose 2, x to the power n minus 2. Now h squared divided by h, we'll just get left with 1h, then plus a h to the power of n minus 1, because h to the power n divided by another h will just be n minus 1. However, if we now consider what will happen as h goes towards 0, the terms here onwards, because they have a h in them and they're being multiplied by the h, they will disappear and shrink down to nothing, because anything multiplied by 0 will be 0. And so the only thing we're going to be left with as h shrinks to 0 is the term independent of h altogether, which is a n x to the power n minus 1. And so just to summarize this again, a key result is that the gradient function is a n x to the power n minus 1, where the actual original function f of x is a x to the power n. So once again, the constant term just multiplies through and just remains unchanged. The power of x gets brought to the front, and then the power of x gets reduced by 1. So very similar to what we had originally, where it was just fx equals x to the power n. So we're now going to use these results in some examples together. So some worked examples, we've got a, b and c. Find the derivative function f dashed x, where f of x equals the following. So all we need to remember is that the power of x reduces by 1 and the power of x multiplies the original coefficient at the front, if there is one. If not, we can consider it as an invisible 1. So for a, f dashed of x, that 10 will be brought to the front. The power of x will just reduce by 1. 1 less than 10 is 9. It's as simple as that once we know the general result. For b, same idea. The original power of x gets brought to the front and multiplies the original coefficient. And so 3 times minus 4 becomes minus 12. And this original power, take 1. 1 less than minus 4 is minus 5. And for c, we need to just neaten this up slightly. F of x, if we've got x on the numerator and the denominator is x cubed, then we can say that's x to the power minus 2. So the whole idea of being able to simplify indices now comes into its own. This is one of the main reasons why we need to know how to simplify indices down. So once we simplify this into x to the power minus 2, we can now say that the derivative function, in the same way as before, this power is going to get brought to the front, so we have minus 2x, and 1 less than minus 2 becomes minus 3. And so that's just showing you the general pattern and how it works in some practical examples. Slightly harder, now we're saying the derivative is dy by dx, which is exactly the same as saying we're going to be finding f dashed of x. It's one and the same thing. So yet again here for part A, we need to neaten up our f of x. So x times x to the power 4 is x to the power 5, and x to the power minus 2, again, we can just subtract the powers using the laws of indices. When we're dividing indices with the same base, we subtract the powers. So we have x to the power 5 minus minus 2, which is x to the power 7. So when we differentiate, when we find the gradient function of x to the power 7, we bring the 7 to the front and subtract 1 from this power. So we get 7x to the 6. That was one of the worst lines I've done all year. That's absolutely awful. Let's try that again. There we go. Still not the best line, but, well, that was just awful. Anyway, never mind. Let's move on to something more positive. So part B, differentiating 4x over the root of x cubed. And so again, let's just neaten up our original function. We've got f of x is 4x over the square root of x cubed. Now the square root is the same as to the power half. So x cubed to the half is x to the power 3 over 2. So that's the same as 4x to the power 1 minus 3 over 2. So that's 4x to the power of minus a half. So therefore, if we differentiate this, f dashed of x, we bring the power to the front, and so this is going to multiply the original coefficient. And so 4 multiplied by the minus a half, that's going to become minus 2. And the new power of x we're going to reduce by exactly 1. So minus a half minus 1 becomes minus 3 over 2. And finally, part C. So if we just neaten this up again slightly, we have for f of x is the square root of all of this. So the square root of 49 is 7, and the square root of x cubed, like I said before, the square root is the same as the power half. So x cubed to the power 1/2 is 3 over 2. So if we differentiate this and bring the power to the front, 7 times 3 over 2, that's going to become 21 over 2. And the new power of x is going to reduce by 1. So 3 over 2 minus 1, we're just going to get 1/2. And so that's these functions differentiated. We're now going to have a look at differentiating quadratics. So worked example 3, we can differentiate a function with more than one term by differentiating the terms one at a time. The highest power of x in the quadratic function is going to be obviously x squared, and so once it's been differentiated, the highest power of x in the derivative will be just x. And so for this example, we've got f of x is 4x squared minus 8x plus 3. We need to find the gradient when x is 0.5. So the first thing I'm going to suggest we do is just to work out the gradient function. And so we consider this term by term. And so 4x squared, if we differentiate 4x squared, bring the power to the front and multiply it by the coefficient. So 4 times 2 gives us 8. The power of x reduces by 1. X squared, knock 1 off the squared, we get x to the power 1, so that becomes 8x. The next term, we had minus 8x. And so that's x to the power 1, of course. So bring the 1 to the front, multiply it by the coefficient. 8 times 1 is just going to be 8. And then we're going to have x to the power 0, which is just 1. 8 times 1 just gives us 8. And so the second term in the original quadratic differentiates to minus 8. And as we said before, when we differentiate a constant, we just get 0. 3 is a constant, so when we differentiate this part of the quadratic, it's going to vanish altogether. And so the gradient function is just going to be 8x minus 8. So now what we can do is we can just substitute in x being 0.5. So therefore the gradient when x is 0.5, so just highlighting here that we're using x as 0.5, that's going to be 8 lots of x, so 8 lots of 0.5 minus 8. 8 times 0.5 is 4. 4 minus 8 gives us minus 4. And so when x is 0.5, we're going to have here that the gradient is negative 4. Part B, just putting what we had as the original result from part A up here, just to remind us. Let's find the coordinates of a point on the graph where the gradient is 8. And so we need to just set here the gradient of the graph f dashed of x. We've been told we need to find where it's 8. And so now if we use this and substitute in f dashed of x is 8, 8 equals 8x minus 8. Now this just becomes a simple equation to solve. So add 8 to both sides, we'll get 16 equals 8x. Therefore, obviously, dividing through by 8 yields that x equals 2. But of course we don't want just the x coordinate, we want the coordinates. So therefore, the coordinates are going to be 2, then comma, 4 lots of 2 squared, minus 8 lots of 2, plus 3. And so if we just work this out here, 4 times 2 squared, that's going to become 16. 16 minus 16 is 0, plus 3, we're going to have 3. And so the coordinates where f of x is 8, has a gradient of 8, is where x is 2 and y is 3. Finally, we're going to look at part C. We need to work out the gradient of f of x at the points plural, where the curve meets the line y equals 4x minus 5. So we need to set f of x equal to 4x minus 5 and then solve the quadratic which comes from this. So the first thing we need to do, if I just scroll down slightly, we're going to solve this here. So we're going to set 4x minus 5 equal to f of x, and f of x, if I just remind you, is 4x squared minus 8x plus 3. And so we need to just rearrange this now into the standard form of quadratic so we can solve it. So then we have 4x squared, subtract 4x from both sides, it's going to give us minus 12x, plus 5 to both sides, we get plus 8 equals 0. Now I'm going to put a big red asterisk by this. We're going to return to this in a moment. But let's just forget we know of this invention called a calculator and see if we can solve this without. So look at these coefficients. We can divide through everything by 2, which gives us 2x squared minus 6x plus 4 equals 0. See if we can factorise this. So using the AC method, 2 times 4 is 8. So can we think of two numbers which multiply to 8 yet add to give minus 6? Well, hopefully we can. The two numbers that multiply to give us 8 and add to minus 6 are minus 4 and minus 2. So we can partition the minus 6x term into minus 4x and minus 2x, finally plus 4, which equals 0. This will now factorise, so we have 2x, x minus 2, just factorising the first two terms here. And these two terms, we've got a common factor, we can manipulate this to be minus 2 and x minus 2. The objective is to have a duplicate bracket so we can put these two things together. That equals 0. So we've got 2x lots of a bracket minus 2 lots of a bracket. We can then say we've got 2x minus 2 lots of x minus 2. So therefore, solving each bracket to be equal to 0, we have x equals 1 or x equals 2. So what I've been hiding from you here is this Desmos little help bit. So we can use Desmos or a similar graphing solution online to do this hard work for us, especially if working from home. We've got this luxury of using a little aid to see if we're on the right tracks. It's a great tool, Desmos, as is GeoGebra. So why not use this to just see on the right lines? So if we have a look here, our solutions are x equals 1 and x equals 2. Now, I did mention about this asterisk here, so just if you want to go to the dark side and use your calculator, just a refresher on how you can use your calculator to solve quadratics. So what we're going to do here, we're going to press menu, scroll along until we get to equation/func, press equals. It's a polynomial. A quadratic is a polynomial degree 2. And we could have, if you wanted, just typed in the coefficients of a, b, and c as they are. And so using the general form of quadratic ax squared plus bx plus c equals 0, our a here is 4, our b is minus 12, and our c is 8. So if we just type this in, it very generously, as the calculators often are, gives us our solution. So x1 is 2, and x2 is 1. So for two solutions, x equals 2 and x equals 1. However, we're not done. What we want is the gradient at those points, not the x values themselves. So we're not quite done. So first case, what's the gradient when x is 1? Well, the gradient when x is 1 is going to be 8 lots of 1 minus 8. So 8 lots of 1 minus 8 is 8 minus 8, which equals 0. So when x is 1, the gradient is 0, but have a look at what I've just nabbed from Desmos. This is actually what we have here. 1 is the minimum point. As you can see, that's a turning point of the graph. That's a minimum. So it makes sense and is backed up by the algebra that this is actually a minimum point. We now need to just use the same substitution back into the derivative function for when x is equal to 2. So let's just try that now. So f dashed of 2, just scrolling up slightly, is 8 lots of x minus 8. So we have 8 lots of 2 minus 8. So 8 lots of 2, no prizes, is 16 minus 8. 16 minus 8 is 8. And so those are the two corresponding values for when the quadratic curve crosses the line 4x minus 5, just using the derivative function which we've arrived at part A. And so this one here is quite similar to some exam style questions you might encounter later on in the course. So what I'd suggest you try next is these suggested exercises from the textbook you should have at home. So a bit of a double whammy here, but again, you've got lots of time now to do these. Page 263 to 264, exercise 12C. And then if you can complete that exercise for me, page 265, exercise 12D, which is just more of the same, but just going into a bit more depth. If you would like to comment in the comment section for any questions you're struggling with, I might do a viewer's choice and go for a few of the hard ones together from these exercises. But the onus is on you, okay, to develop your independent study skills and try and work at home on your own accord. I can't be here with you in class just nudging you consistently to try these questions for yourself. So which camp are you going to be in? You're going to do the bare minimum or push forward and do your best trying all of these questions on the exercises. Okay, anyway, lecture over. Thanks for listening. Leave comments in the comment section below. I'll see you again next time we do a recording. Okay, take care, be safe.